So good afternoon, good morning again. Hope everybody's doing well. We're going to throw in lecture 5, and I apologize, they're sort of out of order. I put a lot of stuff for unit 6 and homework and the lecture up and didn't have everything up for lecture 5. So we're going to backtrack a little bit and talk about corneal keratometry. We're going to be talking about corneal topography. And today we're going to focus a little bit more on the topography just to explain corneal curvature, what it looks like, what a map looks like. And then we're going to do more keratometry later on in the semester because we're actually going to learn how to use a manual keratometer. And all that we're doing at this point is we have done anatomy. We've done how a gas permeable sort of works. We're looking at how contact lenses that are soft drape over a person's cornea, but we need to get into the actual shape and contour of a cornea. We know that the average power is 43 diopters, and as we did the conversion, if we have the index of refraction and you have the power, you can find the radius of curvature, how steep or how flat a lens is, or a surface is. We can do a lot of the corneal measurements in millimeters in radius of curvature. But to make it easier, we transform it into diopters so we can see what is a 43 diopter curve. Steeper would be 44, flatter would be 41. It's easier for us to visualize diopters. However, we do have to take measurements on what it looks like, what is steep, what is flat, what happens if you have a different curvature in one part of your cornea versus another. And as you can probably imagine, if I have one part of my cornea that happens to be steeper, say vertically, and another part that is flatter, well, you still have that clear refractive surface, but it's actually going to project different powers onto different parts of the back of the retina. And that's why we generally will have cylindrical lenses that have both a sphere power and a cylinder power. You need more if I have a different curvature in one part of my eye than I do in the other meridian in the same eye. Then I will probably have to have an eyeglass lens that has a different prescription in one part than we do in another. Therefore, if we have a -1 with a -1 axis 180, you've got a -1 in one part, and then 90 degrees away you have the sphere and the cyl, so it's a -2. Well, that's oftentimes because of slight asymmetry in folks' eyes. So how do we measure that? One of the most important things in contact lenses and ocular anatomy is we have to establish the shape, how steep, how flat, how much astigmatism is in there. So what we're going to do today is talk a little bit on this little PowerPoint that I posted and just go through it really quickly. And so this is, let me go all the way up. Let me go to the very first slide. And so keratometry, we'll start with keratometry. And keratometry is simply taking a device and we're going to reflect light off someone's cornea, these little mires. And when we shine the light, it's going to form a reflection, and then we're going to sort of line up a series of reflections, and based on cord length, based on curvature, based on how far away we are from the patient's eye, we can actually establish what a radius of curvature is, or essentially how curved, how steep, how flat is this person's eye. We can actually determine what sorry for that, about 30 seconds and I realized I didn't share my screen. Who brought the cool kid? So at any event, so we'll start with this lecture here. Sorry about that. This is what we actually gave you guys. And so now you should be able to see this here. So keratometry is simply the measuring of how steep, how flat is a person's eye. How much astigmatism, how much is the difference between one meridian and the other, what orientation. And if you'll start to recognize that the relationship there, we're going to start looking at, we know with our lenses we can identify mixed astigmatism. We can identify compound and simple hyperopic and myopic astigmatism. Well, now we're going to start seeing how that actually matches up with corneal shape. And to be honest with you, a large percentage, a large majority of the astigmatism in a person's eye is based upon the shape of a person's eye, how steep it is in one meridian versus in another. So keratometry is simply taking a device, and we have a bunch of manual keratometers, which means we actually align and read some devices, just like you have your manual lensometers or your manual vertometers in eyeglass lab, where you'll put the lens in and you'll spin a few dials and try to line some things up, and you can tell me what the eyeglass prescription or what the refractive power of a lens or a pair of glasses are. Well, we're going to do the same thing with the keratometry. We're going to measure someone's cornea, how steep, how flat, how much astigmatism, or how much of a difference between different meridians, and how is it oriented. So we're just going to shine some lights, some mirrors, some targets off the anterior surface of the cornea, and we're going to line them up. And again, we can find out how steep they are. We can find out what the orientation or what the principal meridians are. Problem is there's only a small area with these manual devices that we're using. We're going to have two sets of mirrors on the vertical and two sets of mirrors on the horizontal, and we're going to line them up. So essentially you're only just looking at a few handful of small little areas. So this is actually one of the very first ophthalmometer, and that's the older version of a keratometer, or measuring the cornea. It used to be called an ophthalmometer, which was measuring the eye, but since we can measure the inside, the outside, we changed it to a keratometer. But this is the original design. And if you look carefully, this is our current one that we use in 2021. And there's really, frighteningly, not a huge amount of difference in the makeup of the devices. So this is the same thing that we use in manual keratometry. Now, what it does is it measures a curve at a very specific point on the cornea, specifically in about the central 3 millimeters or so, depending on how far away you are. It doesn't measure the shape. And the reason I bring this up is we have folks that have a certain curvature centrally of their eye, but it flattens to the periphery. We've talked about that. Well, I could have someone that has a cornea that's a specific shape, but it flattens more. And then another person who has a very similar central corneal curvature, but it flattens more or less. So the whole overall shape may be dramatically different, even if the numbers are similar that I'm reading off of this keratometry. So this is only sort of a rough estimate, if you will. It averages, it estimates the average central curves. It's not exactly. It measures only a few points of the central 3 millimeters. It's not the apex and it's not the periphery. It's about 3 millimeter circle, and it's measuring right at that point. If you have an irregular cornea, let's say they had trauma. Remember, one of the things we talked about in one of our last homeworks was, why would you use a gas permeable lens to create a more regular refractive surface for someone? And we use the example of irregular cornea. It could be trauma from an injury, could be surgery, it could be some type of a disease, like a keratoconus is the most popular one that comes to mind. So what will happen is, if you have an irregular cornea or some irregularity of some sort, this manual device that depends on shining a reflection off of a spherical-ish surface really starts to break down, and it's not as accurate. And it's observer dependent, in my opinion. If I take the corneal measurement, if someone else takes a corneal measurement, there is a little bit of wiggle room there. And if the person's measurement is 45 diopters, I may get 4487, someone else give me 45 and an eighth. There is a little bit of, I think, subjectivity and inter-user or inter-observer variability versus some of the other more automated devices. It's a little bit more, no matter who takes it, you're going to get similar results. So if those are some of the limitations, why do we do it? Well, why is it's easy to use. It's relatively inexpensive. You can pick these up and you buy it once and you have it for 100 years. It hasn't changed. It is also not only, and this is sort of important, this is definitely going to be a quiz question or a homework question, and that is because we're determining the shape based on a reflection off of a surface. The reflection is dependent on having a good tear film. If the eye gets dry, if the eye does not have a good, it doesn't reflect as well, If I don't have a good reflection, I can't get good values. And so I'll be looking at the keratometer, and the Myers, what I'm looking for, the reflections I'm looking for, can sometimes get irregular and wavy while I'm looking at it, and worsening as I'm looking at it. That's generally a byproduct of the tear film literally evaporating, the eye no longer being reflective because the tear film has broken down, and I'm not getting good values. Well, that, even if I'm not getting a good measurement, that's very useful to not to look at the quality of the tear film, and that's important. If I'm trying to take a measurement and I can't get them, it looks good and 3 seconds later it falls apart, I know that that person's tear film is not in good shape. And even though I'm not getting a good measurement, it helps me look at the quality of the ocular surface as well as the shape. It's okay at detecting abnormalities. I can't sometimes determine what they are, but I can see when they're there. But especially if they're centrally. If you have some abnormality or scar that's off to the periphery, I may not see it as well. And a lot of times this just gives me a starting point when I start doing my diagnostic or trial lenses. If it's really steep, I file a steeper contact lens. If it's flatter, I will choose a flatter contact lens, especially when we're talking about gas permeables. If I pick the wrong one, at least it's just a starting point. I don't need lots of fancy materials just to give myself a starting point. I can always evaluate the lens, see if it fits, and if it doesn't, make adjustments. So again, cost efficient, relatively easy to use, those types of things. And I can also monitor change over time with any keratometry measurement. Now again, these were the limitations again. So this is what's called an autorefractor autokeratometer. This is a device that if you look at anybody who's ever had an eye exam, one of the first things they do is when you sit in on the table for the doctor's office, they have you look into a little machine and you see either a hot air balloon or a farmhouse at the end of a road. And what that's doing is giving you a fixation target. And this machine helps us determine the approximate refractive error of a patient before they ever tell the doctor which is clearer, 1 or 2, to refine the prescription. That's called an objective autorefractor. Now, this machine also will bounce lights off of and measure the corneal curvature, but we are not using a manual device. This is an automatic. So this is quite frankly just called auto keratometry. And if you've ever gone to an eye doctor, let me put this down and let me see if I can show you a photo of what the actual printout looks like. Um, so let me move this out of the way. And this would be a printout that would be normal for an autorefractor. And this tells me what the date was, what patient number I had. Let me make sure I'm still sharing this. Let me share it again. There we go. Sorry about that. So this right here is the autorefractor slip that would print out if you ran this at an optometry or an ophthalmology office. And again, it gives me the date, the patient number. The VD is the vertex distance. Do you remember? We've been talking about vertexing a prescription in eyeglasses. You'll consider vertexing any pair of glasses that's over plus or minus 7 diopters. Remember, in contact lenses, once we start getting over plus or minus 4, because we're changing the vertex distance from where the 4-opter was to where the contact lens is, it makes more of a difference. So we have to start doing it at lower powers. So anything over plus or minus 4, we have to start doing the vertex distance compensations. And this would be the number that we would use, the 13.75. This is my vertex distance. And this is what we would use for our compensation numbers. I'll never have you assume what it is. I'll always tell you what it is. So in this case, if I asked you if this was the eyeglass prescription that it generated, and this autorefractor gave me an approximation of this person's prescription, minus 325 with a minus 2, axis 4, and if I said let's vertex this for contact lenses, we would use the original 4-opter of 13.75 for the vertex distance for refracted. We would use 0 for vertex distance for the contact lenses. So the difference, we moved it from the eyeglass prescription to the contacts would have been 13.75. It's much easier than in glasses. Minus 325 minus 2x is 4. You guys know that this is a compound myopic astigmatism, and it's within 30 degrees of 180, so that's a with the rule. There's a lot we could tell. You can tell me that the sphere power is minus 325. The total power, which is your sphere plus your SIL, would be minus 525. All this stuff is things that you've been learning, but now you see these practical applications. And so it gives me an approximation of the right eye prescription and the left eye. This isn't my eyeglass prescription. This is what the doctor will use, and then start putting the phoropter, flipping lenses, and trying to see if they can fine tune and adjust and improve to make sure it's the exact right eyeglass prescription. Again, this also, minus 3 with a minus 1, it gives us a spherical equivalent. You can either take half of the SIL and add it to the sphere algebraically, or take the sphere and the total power and take the average. Either way, don't care. It's a minus 350 spherical equivalent for this left eye. But what I would point out is, take a look down here, and in the right eye, I have a horizontal meridian, has a 40, at axis 10, if you're looking at a lens cross, axis 10, it's 42.75 diopters. And then notice vertically, it's steeper. There's a difference between one meridian and the other. And in the right eye, the difference is about 2 diopters. If you'll curiously enough look in the right eye, it's saying that there's about 2 diopters of astigmatism, and that generally matches up pretty well. If the difference in the corneal curvature is around 2, it's a safe bet that oftentimes the amount of astigmatism in that patient's eye will also be about that same amount. And we'll start to look at this in the left eye. This was the right eye. They don't have my left eye numbers here, so we'll skip over to their horizontal meridian. So we'll skip that. This just is the right. But notice also that we can correct from the dioptric value to the radius of curvature. And remember, what we use is 337.5 and divide it by this number, we'll get that one. Or if I want to go from millimeters to diopters, it's 337.5 divided by this, and I'll get my 4275. But in this case, what I want you to realize is, one, it was done manually. It was done automatically by a machine. We didn't have to twist any dials. We just popped a button. Secondly, if you look at this, I can tell that at 10 degrees, this person, the cornea has a certain curvature, and then up and down at 100 degrees, it has a steeper curvature. They're not the same. One refracts better than the other. And this is what an auto keratometry is. Now, if I go back to my bottom, there we go. Let's go back to the PowerPoint again. We'll go back to my WebEx. We'll return to the meeting. I'm sharing my screen, very good. So auto keratometry, why don't we just use this all the time instead if it's that much easier? Well, it's easy to use, and actually I'd argue this is probably the easiest of all of them, and we're doing it anyway for part of an eye exam for most offices. It is more expensive though. It costs more for an auto keratometer. It costs more for an auto refractor, and generally they're both in the same machine. You get the approximation of their refraction, and you get the approximation of their corneal curvature all in one report from the same machine. But it is more expensive. However, if you're in an optical office, I've never seen an office, optometry or ophthalmology, that doesn't have one of these in it. If you're fitting contacts as an optician on your own, you may or may not have access to this because you may or may not need it. You may only need the manual keratometer. But if you're fitting in a larger office with more healthcare practitioners, you'll absolutely have access to one of these. Now, it's also faster than manual. Click a button, off you go. Arguably, if you have 5, 10, 15 people, hit this button, it's going to come up with virtually identical numbers every time, all the time, regardless of who hits the button. I feel that manual keratometry, again, there's a little bit of wiggle room there. And again, this will help me how steep, how flat, what shape contact am I going to use for that base curve or the central posterior curve. And again, I always take keratometry either manually or on an automated before I fit a contact lens, and then I look at it over time to make sure I haven't changed anything or it's not changing on me. As always, there are benefits, but there's also limitations. I can't just with manual keratometry, I can see the quality of the reflection in the machine as I'm using it with the Myers. With the auto, I don't have that. I click a button, it gives me numbers, and it gives me no qualitative measurements. It doesn't tell me how good the ocular surface is, but it manually can. This one really, I have almost no ability to see if there's any irregularity, corneal abnormality. It just gives me numbers. It doesn't give me anything else. Relatively limited in diagnostic ability. So if somebody has keratoconus, it's much more difficult to spot that. With the manual, I would have seen a little bit of waviness in the reflections that I'm looking at. This one, I don't have that. So I'm literally going to hit it, get some numbers, and that's about it. This is where I am. Topography. We talked about manual keratometry. We talked about auto generation of keratometric values or auto keratometry. This is topography. This is my favorite. This is what we should all be doing. And we have one of these in lab. We'll do this in our labs when we get our hands-on component. And topography is literally not just taking curvature measurements at one part of the eye, but it's going to give me a topographical map of a person's whole eye. How steep is it in the middle? How steep or flat is it in the mid-periphery? How steep or flat is it in the far periphery? How much does it flatten? How aspheric is it? This is amazing. This is fantastic. We back in the day, years and years, decades ago, we didn't have, nowadays we have computer generated interpretations of our maps, and it'll give me a quick, cool printout. Back in the day, they didn't have that. So they would literally just shine some circular discs on a person's eye and look through and see what it looked like to look for curvature, look for irregularity, guesstimate some measurements, and it looked a lot like this. You'd look through one and it would reflect some reflections off their eyes. We talked about one of your handouts, one of your things that we do for our contact lenses, for our learning materials rather. It showed a video of exactly how those reflections would change based on corneal shape. So let me show you this little video that we had. I muted the sound, but again, as we're looking through this, any keratometer nowadays generally uses these concentric rings. We call them placido rings. Just like in our PowerPoint presentation, we used to do a little handheld version of this. And as you're looking at it, if I reflect all these concentric circles off someone's eye, depending on if it's, say, steeper side to side and flatter up and down, the shape of the reflection is actually going to change. And what will happen is if it's flatter up and down and steeper side to side, the steeper it is, the closer together the lines and concentric rings will be. The flatter it is, the farther away they're going to be. And what's really cool about this is if you have some type of an irregularity, like keratoconus, what'll happen is I get this sort of drooping or poking out of or irregularity there. And if I'm going to look at this shape, they don't look like concentric rings. It looks like I can tell the irregularity just by looking at the reflections off this person's eye. Now, years and years and years ago, this was something that was more difficult to sort of guesstimate. Well, nowadays we have the machine will actually assign values to these curvatures. And so if we went back to this curvature that was flatter up and down and steeper side to side, if you were to look at this overlay, what they do is they put this cool little map underneath, and it's sort of harder to see because they wanted to overlap both the pattern and the map. But what's happening is they have the red colors horizontally because these are steeper, and this cornea is going to be steeper here, and this cornea is flatter up and down, and so the colors are more cool. I've got the blues and the greens here, and the hotter colors are reds and oranges and yellows. So I can look at this and tell that this meridian is steeper on this patient's eye. This meridian is flatter. Well, I could have seen that with just the reflections, but now I have a computer or a topographical printout of that. Same thing with this irregularity that we were talking about. Here we have this bulge here, and you can see this irregularity, but in order to actually visualize it, we can actually put a map to it. And underneath, you can sort of see it's steeper here, flatter up here, and that corresponds with this. And so now, instead of taking a measurement centrally and just having two sets of numbers, I can actually get a whole map of the shape, the size, the contour, and this is really the way you should be doing it with certain specialty contact lenses. So we'll get rid of this here. I just wanted to show you that's a neat video just to visualize it. And again, going from how they used to do it, handheld, to now doing a computer, and back in the 1980s is when they started using computer mapping using that same device, the Placido rings. And you're using the same issue. They're concentric lighted rings, but now the computer is going to interpret them for us. And this is sort of what it looks like if you were a patient looking into it. Here you have the illuminated rings. They're all concentric. They're all perfectly round. And then how they are warped, changed, or the appearance changes, the computer is going to read that and sort of try to give a printout. Again, if I were looking through, I could see that there's some irregularity here. They're not perfectly round. And that's how it was. Now, most reflective topographers use this Placido disc or concentric circles. Some use a grid pattern. And I will say that this needs to be, just like we had the manual keratometer, it relies on having a nice, smooth, reflective surface. So if we have any anterior surface disease like dryness, if we have patchiness, these don't work as well because there's no reflection. If it's dry and there's not a liquid tear to reflect off of, we're not going to get good results. But again, these are what it would look like with different types of corneal shapes. You can sort of get an idea of what you think it may look like. Now, typical topography map. This is what, if you ran the test, this is what a topographical map looks like. And in this case, it's steeper up and down, obviously, and flatter back and forth. And cooler colors, blues and greens, are flatter. Warmer colors, yellow, red and orange primarily, tend to be the hotter or steeper colors. So if I ever asked you with this view here, which meridian is steeper, you would tell me the up and down or the red or the vertical meridian. Which one is flatter relatively? Well, if this is steeper, that would leave this horizontal to be flatter. This is cool because in the little printout I can see how big or how small the pupil is. That's fantastic. Very useful. And what it'll also do, despite the fact that I have this cool topographical map, it'll also give me the simulated Ks, or what reading would I have gotten out of an old-fashioned automatic auto-K or manual keratometry. That way I can sort of shift back and forth just to get an idea. But this topography for me gives me much, much, much more detail. And if it were up to me and you're fitting any specialty contact lenses, this really is a no-brainer. You really should have a topographer. Notice how this view is all messed up. I don't have any reading here. I don't have reading here. I don't have reading here. This is indicative of a dry eye. There was no reflection off the anterior surface. And I'm not going to get into the different views right now because there are other different technologies like a pentacam, horizontal slit scanning, ultrasounds, Scheimpflug, but there are other cooler ways. Instead of just a reflection off the front surface or anterior surface, we can actually take OCT or optical coherence tomography. This is cool. I'm going to take a little sidebar, if you will. This, as you guys recognize, here's my optic nerve, here's my fovea and my macula, and this is a device that we can take photographs and images, and What's interesting is that the retina has multiple layers, but we can only see the very front when we look in there. Well, we do have devices that we can take a cross section and sort of like look inside the eye. So if you were to take a cross section of this eye, almost like pretend you had the retina and then you froze it and you chopped it down the middle and then looked at it from a side view, that's what this machine does. This is an OCT or an HRT in this case. And I can actually see all the individual different layers of the cornea. Here's a nerve fiber layer. The cones and rods and cones are in this area. This is the choroid. So I can actually look at how healthy this is. Well, not only can ophthalmologists and optometrists look at and analyze and test the health of someone's retina, but we can also do it with the cornea or the anterior segment. And it's really cool because some of these fancier designs not only measure the steepness or curvature of the front part of the cornea, which is what general topographers do and manual and auto keratometry do, but it also gives me how steep or how flat is the posterior. This, you can see this is part of the crystalline lens. There's all these things, and this is a little fancier than what I need to get into now, but I just wanted to give you a taste of what some of this cool stuff looked like. So we're going to skip some of these slides because it's a little bit more than what we need right now, but be aware when we're talking about keratometry, manual or auto, it's reflections off the front surface. Traditional topography is a reflection off the front surface like this, but there are devices that are significantly fancier and will give me, like this is a cross section of, this is the curvature of the front surface of the cornea, the back surface of the cornea, the iris, and I can actually see the shapes of the crystalline lens from where I can see through the pupil. There are some fancy devices that we can get and use. Just like they had the OCT of the retina, well, this is actually an anterior segment or cornea, iris, crystalline lens, and it's a cross section. These cool machines are a little bit above and beyond what we're going to be doing this semester. But again, I just wanted to show you, these are great for fitting specialty lenses or scleral lenses, if you will. These are fantastic. There's a lot of stuff that we could measure here. But again, we're going to keep going on. This is a great picture that I love. We used to only be able to take a OCT of the retina, or we could do the anterior segment, but a few folks have taken series of images and posted it all together, and instead of a cool little picture, instead of a cool little diagram or color coded, this is an actual scan of a real human eye. And you can start to see the interactions of, here's the cornea, thinner here, thicker off to the edge. You can see the transition between the clear cornea and the opaque sclera. You can see the iris, the crystalline lens. You can see the vitreous here. And what's really cool is the retina. Remember we talked about how many, all the, right through here are the photoreceptors, and there's a higher incidence of cones here. And then as you get off to the periphery, there are fewer photoreceptors and less retinal tissue. So now there are, obviously you want more of the photoreceptors here than you do out here. And so this gives you, and this is where the optic nerve, where when light goes all the way through this structure, triggers a response. It then comes right back up, goes down some little axons and some little nerve fiber layers, and goes right to the brain. And again, here's my choroid behind. This to me is maybe one of the coolest pictures you'll ever see. You can see the extraocular muscles as well. So this would be a left eye looking down from the top. Medial rectus, lateral rectus, optic nerve. Very, very cool. But at any event, this is cool technology. And again, this just verifies what we were doing in ocular anatomy and physiology. Typical topographical map. Let's go back to this. Steeper up and down, flatter side to side. This is important because we talked about with the rule and against the rule eyeglass prescriptions. Well, if most of the astigmatism is produced from an different corneal curvatures, well, it should stand to reason that we should be able to look at a cornea and determine whether it is a with the rule or against the rule cornea, just like it's with the rule against the rule eyeglass lenses. Now, what I'd like to do here So what I wanted to point out is when we talked about, for Unit 6, and we're doing with the rule, against the rule, I wanted to show you this little lens cross assignment that we had. This is what we're doing in lensometry. Let's say I had a lens that was a -2 sphere with a -2 sill, -2, -2. Well, the eyeglass lens would have a -2 throughout the entire lens, and then 90 degrees away from wherever we set the axis, it would have an additional -2 sill. So it would be the two primary meridians would be a -2, and then add the sphere and sill together, or in this case a -4. So this lens, if you look at this blue lens, it would be a -2 here and a -4 here. And so I could actually move it any way I wanted. This is what, when we are doing lensometry with loose lenses, this is essentially what you're doing. A -2, as you can imagine, is going to be a little on the thick side here because it's thin in the middle, thicker to the edges. But because it's got astigmatism and it's a compound myopic astigmatism, and a -4 is going to be thicker on the edge than a -2, and they both have the same center thickness, well, you can imagine that this is going to be thick, but this is going to be thicker. And this is more minus up and down, and more less minus this way. Well, I can actually, depending on how the doctor asks me, I can set it this way. I can set it this way. So this would be a -2, -4. I'm sorry, a -2 with a -2 sill, axis 180. This would be a -2 with a -2 sill. We haven't changed the lens at all. We just changed the orientation. This would be about 45. This would be about 90. Well, what's interesting is notice how, if this amount of astigmatism that we have was caused by differences in corneal curvature, here's my -2 here, here's my -4. One of the things that causes more myopia is a steeper cornea. So let's say the eyeglass prescription was like this. I have a -2 up and down and a -4. I was a -2 back and forth rather, and a -4 up and down. Well, if a steeper cornea causes more myopia, my question to you would be, which is steeper, which one's flatter? Well, whichever one is more minus is going to have a steeper corneal meridian associated with it if the eyeglass prescription and the corneal curvature match up, which they generally do. So in this case, I would have a -2 here and a -4 here, or a prescription here and a more minus up and down. And if it is a more minus up and down, I would expect the corneal curvature to be steeper up and down, or a corneal topographer to be a hotter color up and down. So if this is a with the rule eyeglass lens, then it would stand to reason that this picture here, steeper up and down, is an example of a with the rule corneal curvature. Now, if I saw something like this, it's steeper side to side, flatter up and down. Well, if that were the case, then it would probably look a little bit more like this. The higher minus would be side to side, the less minus would be up and down, so the corneal curvature would be hotter here or steeper here. And this is -2, -2, sphere goes with the axis. This is an against the rule eyeglass prescription. Therefore, this would be an against the rule corneal topography. Now, I will tell you that if you, again, you can look through this, you can learn it, you can memorize it. If you're ever in trouble, I'm going to give you my sort of pro tip, and that is this up and down versus this steeper side to side. This looks like a bow tie if you were to look at a tie, and this looks like a regular tie. Well, if it's a regular tie, it's with the rule, and if it's a bow tie, they're little weirdos once in a while, so that would be an against the rule. If you're having trouble, just remember, side to side, bow tie, against the rule, up and down would be with the rule, and obviously if it was curved at a 45 or 135 angle, that would be an oblique. So let's keep going here. This, remember with that little demonstration we had, if it's steeper here, not up in one meridian or another, this means there's a isolated abnormality And remember what we said about the average corneal curvature in previous lectures being about 43. Well, if the average is 43, and here I have this huge bump of 64, this is a huge bump or a cone-shaped area off-centered, and this is what we would call keratoconus. And it's a textbook case of a very severe case of keratoconus. I can't correct them with glasses. I cannot correct them with soft lenses. I generally am going to have to do a corneal GP lens or a hybrid lens, which has the soft skirt or the corneal button in the GP button in the middle, or better yet, potentially a scleral. This, if you ever wanted to look at it, these two kissing doves or the butterfly, this is what's called pellucid marginal degeneration or PMD. And I think I'm going to keep going here. If we're talking about corneal curvature, if we're talking about topography, if we're talking about keratometry, I can't help but mention LASIK eye surgery or refractive eye surgery. And there's photorefractive keratectomy, there's LASIK, laser-assisted in situ keratomylosis. It's up there, don't worry about spelling it. And generally the idea is we take a cornea that is too myopic, generally, and we make it less myopic. Well, if an eye is too myopic, and we've talked about a steeper cornea making someone more myopic, the idea is if we can make it less steep, it'll be less myopic. So generally, LASIK is we're going to flatten the central portion of the cornea. If it's flatter, you're going to be less myopic. And so what they do is they take a little laser or a blade and they slice off a little top layer of the epithelium without unhinging it. They keep a hinge there. They don't tear the damn thing off. Then they zap it with a laser and it changes the shape and makes it centrally flatter. And they put the hinge back down, the flap back down, and it'll attach right away, but generally over a number of months, it'll heal right up without any sutures or glue. And now we've reshaped the front of the eye. And that essentially is how we go for people who are highly myopic. They get LASIK and now they don't require eyeglass lenses. It's not contacts, it's not glasses. We've just reshaped the eye centrally so that they're less myopic. And notice how steep, flatter, it would have been much steeper before, but we flattened it. And this is what it would look on topography, which is really cool because remember, I've got some somewhat steeper colors, but now I have a very flat area. Remember, cool is flatter. So I have this island of flatness. This is what someone who's undergone LASIK will look like. It's almost like a plateau. It's a little curved and then nice and flat. And these are obviously doctored. It's not perfectly flat. It's not zero, but it's flatter relative to. And again, these are what these look like. We will get into briefly later on in the semester, later on in the year rather, later in the program, we do what's called ortho-K, orthokeratology, corneal reshaping therapy. And this is where we actually use GP contact lenses, gas permeable contact lenses, but we actually shape them in such a way that it's almost like using Invisaligns, but for your eye. We put a molded contact lens, slap it on the eye. It's going to reshape the eye so that it looks just like this, flatter in the middle, steeper off the edge. And if you can do this, it'll actually reshape the eye so that you're less myopic. It's really cool. The difference with LASIK, if you hate LASIK, too bad. This one, if you don't like ortho-K, you just stop wearing the Invisaligns for your eye, or you stop wearing the molded contact lens, and it'll go right back to normal. This is also important because ortho-K may, not only just correct somebody's eyes vision, so that they don't need glasses or contacts, but it may actually slow children who are developing myopia, and it may make them less nearsighted as adults if we start them early enough. Bizarre. We'll get into more ortho-K later, but I wanted to talk a little bit more about the the measuring the topography. And now, because we're doing more stuff with things like scleral lenses, which are not just centrally located, but they're really going off to the edges, we're now having these topographers that will take additional measurements, and not just corneal measurements, but corneal, limbus, scleral curvature. And you can start to see how cool this is and how we can measure how steep or how flat someone's eye is. And the whole not just with corneal care. Remember, keratometry is just measuring a 3 millimeter and gives you a rough approximation of how steep it is. This shows me how steep it is, how flat it is, where the limbus is. I would argue topography is really where it's at. And again, we have more and more technologies where if I'm trying to do scleral lenses, I can start doing different types of maps. I can start to design scleral contact lenses, how it's going to fit, how we can vault it over the eye, and much better than a traditional manual keratometry reading. And then the last thing I wanted to show also is with specialty contact lenses, we have stuff like a keratoprosthesis, which is a fake cornea that they can suture on there. Sometimes we'll have to do corneal transplants. Well, if those don't work, sometimes we'll have artificial corneas. And again, we can measure what this looks like and start fitting specialty contact lenses over it to make sure that they see better depending on how it is. So there's a lot of stuff we can do, but I just wanted to go over and the basics with keratometry, the basis of topography. And again, some of the take homes are, if I were to give you a reading, you should know that the curvature of the cornea flattens to the periphery. You should know how ortho K or LASIK will make somebody less myopic. I should be able to show you a picture of either keratoconus or the kissing doves or butterfly shape of a pellucid marginal degeneration, and you should be able to identify it. I should be able to give you a topographical map, and you should be able to tell me whether it's against the rule, with the rule, or I could give you a bunch of eyeglass prescriptions, a bunch of corneal curvatures, and you should be able to match up which one goes to which. What a great test question. I want you to be able to look at these here and see how the eye actually looks. And then I want you to know the pros and cons of keratometry, topography, et cetera, et cetera. So normally I'm trying to keep these at about a half hour a piece. I've gone a little over that. This is closer to 40, 45. So you may want to take it into smaller bits and pieces. But this is really maybe one of the most important things we do with contact lenses, because we need to know the shape, we need to know the curvature, we need to know what fits on that eye, and I don't know what fits on the eye until I know what it looks like, what shape it is, how steep or how flat it is, how much astigmatism it may have, and what this is going to mean going forward. So at any event, thanks guys very much. We'll post this up online, we'll give you some more homework, and then pretty soon we'll actually teach you later on how to start using these. By the end of the semester, I want you to know how a keratometer works, at least virtually, and then starting next semester in the fall, you guys are actually going to measure one another, and you'll start measuring people's corneas using a keratometer in lab, so we can start designing contact lenses for real people. Thank you very much. Hope you have a great rest of the week, and we'll talk to you soon.